Hello and welcome back. We have understood linear regression algorithm, how it works, and the solver we used in linear regression, the scikit-learn's linear regression algorithm was normal equation. Right? The normal equation formula is like this: x transpose x whole inverse x transpose y. What is x here? All the input data, right? x0, x1 and so on, xn is the x, the big X, and the y is the output variable, the y target variable, right? So the target variable, whatever data. If you pass this whole data into this equation, in a single shot you will get all thetas. All thetas are theta 0, theta 1 and so on, theta n. Right? Suppose that you have got only one x and one y, one input variable and one output variable, and if your data is spread like this, right, you will get your ultimate theta in a single shot. If you substitute your data into the equation, you will get in a single shot. That means you will get this line. When you are getting theta, what is theta? Y cap is equal to theta into x is the formula. What is this theta? Is the line, right? The coefficient actually decides the direction of the line, the slope of the line, right? So in a single shot you will get it. But the problem with this formula is that if your data is huge, if you have 1 billion records, you cannot execute this because this whole calculation happens in your memory. The second problem with this algorithm is the dummy variable trap. If there are two or more columns which are strongly positively or negatively correlated, 1 or minus 1, then this x transpose x becomes a singular matrix and there is no inverse for singular matrix. So the thetas you got, or the thetas the algorithm is deriving, are not proper, right? So to avoid these problems, we will actually depend on the algorithm called gradient descent. So let us try to understand how gradient descent works and how exactly it can solve these problems. So in the gradient descent, it actually instead of learning everything in a single shot, it learns periodically. It learns some theta, which is nothing but a line. Your original data is somewhere here, and it actually started with some random line and then moved that line a little bit, moved that line a little bit, moved that line a little bit. Like that it's going to move and reach to the ground. Instead of single shot learning, instead of putting all your data into the normal equation and learning the coefficient in a single shot, you are taking some coefficient, some random coefficient, and slowly moving towards the global minimal error theta place or the best fit line place, right? So this is called as a gradient descent algorithm, and it periodically learns the theta. So how exactly it works, we'll try to understand. Suppose that your data is like this. You have got only one x and one y. Your hypothesis function becomes like this. There is no theta 0 also. We have taken only one x and one y, and the equation is theta x. Okay. When there is only one x and one y, you can actually represent that on a two-dimensional plot. So your data is like this, suppose, right? You need to find a best fit line which goes through this data. So how gradient descent algorithm works is, it starts with some random theta. Suppose that the theta is equal to 6. Okay. So what is the y cap formula? Y cap is equal to 6x. If you substitute all your x's into the 6x formula, you may get a line like that. Okay. Example line, right? It should go through origin. So maybe let me correct this. It should go through origin. Right. So let us take this thing, and then it will go like that. The line will go like that, 6x. Okay, depending on x, it actually kind of depends the thing, right? So it goes through, it goes like that, right? What we need to find? We need to find the best fit line or the theta associated with this green line. Okay, we need to find the best fit line, the green line we need to find. So to do that, what gradient descent algorithm will do is, it will actually move this line like that, right? And then like that, and then like that. We don't have intercept, so it is the line is always going through the origin, right? And then it will move like that. So it will actually change the theta. The gradient descent algorithm tries to play with theta. The 6 will change to 5, 5 will change to 4, 4 will change to 3, 3 will, like that. It will actually try to play with theta and move towards the global minimal error place or the best fit line place, the green line place. So to move like that, right, we need some basis, right? When I drew this line, the y is equal to, or y cap is equal to, here the y cap is equal to 6x line, right? I know it's a random line, right? Initially the gradient descent chose a random line, and then it is trying to move towards that green line, right? That global minimal error place it is trying to move. So it should know the direction, right? It should know the direction in which it should move. The gradient descent algorithm should know the direction that it should move in this direction only, and it should stop here. It should not surpass this line and go, right? It should stop here. So those two are the points the gradient descent algorithm need to do. So those two things should be done numerically or mathematically, right? So to do that, we will take help from the cost function. If you look at this cost function, it is y cap minus y whole square. It's a squared error, right? From sigma I is equal to 1 to m. There are m number of records and we are calculating the error like this. So what is y cap? It is theta x minus y. That means what? Here if theta is 6, it is 6x minus y whole square. Sigma I is equal to 1 to m, right? So if your x is all substituted into this formula, you will get some error, right? Suppose that error is 40. Okay, suppose that error is 40. So what we need to do, when we need to, or the algorithm need to move this line to global minima, every move, right? The next theta may be 5.5. We don't know what it's going to be. We'll calculate it. If it is 5.5, the error from 40 it should reduce to 30. Again, it may be 5, right? Then it should reduce to 20. Like that, it should happen, right? With every move or every change in theta, the error should reduce, right? So we will focus on error to find the direction. So the point here I wanted to make is, the error is giving you a clue on which direction to move. So to make this clue a little more evident, the gradient descent inventors, what they did is, they actually took the cost function, a convex function. This cost function, a convex function. What is the use of convex function? I said that we are playing with theta and we are trying to, see how the cost is changing. J of theta is nothing but cost, right? We are playing with theta and we are trying to see how the cost is changing. If the cost function is convex, if you take different thetas, random thetas, and try to plot the dots, right, the dots will come like that. If you take random thetas, like 6, 5, 10, 20, minus 5, minus 6, minus 8, minus 10, like that, if you try to take different numbers, the dots will come like that. We are taking different thetas, we know x, we know y, we are substituting those values into this, and then we are plotting this graph. So when you plot this graph, it's going to be parabola, because this is actually an x square formula, right? So the second degree polynomial is going to be parabola. Sometimes it is strictly parabola, sometimes it's a bit here and there parabola, but it's going to be parabola, right? So we have got a parabola. What is the use of parabola? When you look at this theta and the j of theta, on y-axis we are saying error, right? So here the error is too high, here the error is too low, right? On this particular data set, right? On this particular data set, when you substitute x's and different random thetas, this is the minimal error you got. There is no error minimal than that. So if you find this theta, let me take another color, right? So if you find the theta which is present at this place, right, you reached your goal, right? So when you choose 6x, that may be somewhere here. Your 6x may be somewhere. Your 6 may be somewhere here. On x-axis we have taken theta, right? So this may be 6, this may be 5, this may be 4, 3, 2, 1, 0, -1, -2, like that, right? So your 6 may be somewhere here. Right? Your 6 may be somewhere here. What we need to do? We need to move in this direction. Right? Well, how do we know? Because of the cost function we know. In the cost function, we have seen that there is a minimal error place for a theta. Okay? If the cost function is not convex, you will not know where exactly you need to move or in which direction you should move. So to find out this direction, what we will do is at this 6 to the cost function, we will take a tangent line. What is a tangent line? It just touches the curve. It will not actually do anything. A line which is touching the curve is called as tangent line, and we will take the slope of this tangent line as helper. What we will do is, now it is 6, right? Theta is equal to 6, 6x, right? So the formula to calculate next theta is equal to theta minus alpha. We will talk about alpha in a moment, right? Forget about alpha for some time, and then slope of the tangent. Okay, so theta minus slope of the tangent. For some time you think that it is theta minus slope of the tangent. Okay, so if you have to find the next theta, right? Theta is equal to 6 minus, if the slope is maybe 16, if the slope is 16, right? What happens? 6 minus 16, right? 6 minus 16 is how much? Minus 10. Okay, so where is minus 10 here? Somewhere out here, right? Minus 10 will be somewhere out here, right? So what happened? From 6 the theta jumped to minus 10, right? Next theta it actually gave minus 10. So this is not we wanted to do. What we wanted to do? We wanted to slowly move towards the global minimal theta, right? Maybe from 6 we may want to come to 5, 5 to 4, 4 to 3. We don't want to jump all the way to minus 10. So to do that, right, not to jump that much, we will take help from this alpha, a constant, a step controlling constant, I would say, right? If you take alpha as 0.1, right, alpha is equal to 0.1, we call this as learning rate, right? We call this as learning rate. If you take alpha is equal to 0.1, if you multiply this 16 with 0.1, how much it becomes? 6 minus 1.6. It is 5.4, right? The next theta calculated is 5.4, somewhere here. You moved from here till here. In another way, right? The error from this place to this place, error reduced, right? When you chose the alpha is equal to 0.1 and calculated the next theta using this formula, you have moved here, right? Let us try to think that the slope here at this new theta, right? Let me draw this again. Right, at this new theta, if your slope is maybe 10, think it is 10, right? Slope will reduce, right? When you have a convex curve like this, right? So slope here will be very high, here will be a little low, here will be even low. If you reach to the global minimal place or the to the bottom, the slope is going to be almost 0, right? You need to remember that, right? So here we moved from 6 to 5.4. Think that the slope is 10, right? What is the next theta formula? Theta is equal to theta minus 0.01 into 0.1 into slope, right? What is the theta here? Current theta is 5.4, right? 5.4 minus 0.1 into 10. It is how much? 5.4 minus 1. It is equal to 4.4, right? So it moved from 5.4 to 4.4 somewhere here. So it again moved, right? From theta, it started with random theta 6 and it is now at 4.4, right? At 4.4 the error is low. See this? At random theta the error is high. At the next theta the error is a little low. At next theta the error is little even low, right? We are actually moving in this direction, right? We are moving. How can I say we are moving in that direction? When you took the second line, the 5.4 line, it is closer to data. When you calculate error, it's going to be low. When you actually drew that third line with 4.4, it is even closer. So we are actually moving in this direction. So this formula is giving you the direction to move, right? The theta direction to move, and your cost function is giving you the clue, and your cost function's tangent slope is the basis on which we are actually moving. Okay, so this is how the gradient descent algorithm works. So let us try to see on a code, on a data set, how we have worked out, a small video on how on a real data set, how it works. Okay, and then come back and try to understand it. So let me open that PPT and show you. So here the line started with 100, a random number 100, and our data is like this. Okay, our data is like this, x and y. This graph is between input and output. This graph is between theta and j of theta. I said, how did we drew this graph, right? Randomly choose maybe 1000 numbers and try to substitute into the cost function. What is your cost function? Squared law, sigma e is equal to 1 to m y cap minus y whole square. Substitute into it, you will get different data points and you just plot it. But that's the graph here. Why are we looking at it? Because the slope of the tangent of this cost function is the basis. If you look at this formula, we randomly chose some 100 and drew this line, and then we are calculating the next theta. What is next theta? Is equal to 100, the current theta, minus the learning rate into the slope. If you practically see, in reality, the slope, see this, it is so high. So you need to take the number, the alpha number, a little very low, because you want to move slowly and come here rather than jump all the way out. Right? If you don't have this number, right, 100 minus this big number will give you a negative number, a big number, and it will go very far. Actual theta you need to reach somewhere here. So you need to use this learning rate to control the step. Our main goal here is to find the best theta or best fit line. When I am saying theta, best fit theta and best fit line, it is just that theta and line are nothing different. It is y is equal to mx is the equation, or theta x is the equation. If you find proper theta, it will go through the line. If you don't find the proper theta, it will go somewhere like this, right? So in the next step, what we did, at 100 we calculate the slope of the tangent, and it is 587,773, and we multiplied it with alpha and reduced it. So from 100 it moved to 70. So in the next iteration, we will calculate slope at 70 and try to subtract that slope from the 70 by multiplying with alpha. So we will find the next theta. So we found next line. Right? Again, we use the same formula. Theta is equal to theta minus alpha into the slope of the tangent at 50. Right? At 50, the slope of the tangent is this much, and we multiplied with alpha and subtracted. Again, we drew the line. Right? With new theta, the 36, we drew the line. How do you draw the line? You are going to substitute y is equal to 36.59261 into x. That's the equation. You are going to substitute all x's into that, and you take the dots and draw the line. Here also the error is going to be high because the original data points are the fitted line is very far from the data points. So let me execute this algorithm again. Theta is equal to, current theta is 36 minus alpha into the slope of the tangent at 36, right? This slope we are subtracting, and we found 27. Okay. So if you look at the derivative of the gradient, the derivative of the cost function at this theta, right? We will see that later. Okay. So again I executed, right, by taking the slope, I substituted into the equation, and I found. So when you see this, right, this line is moving close to the global minimum. It moved a little more, right? It moved even more, right? So we are finding the best theta using the by taking the help from cost function or cost function slope at that particular theta, right? See that the line actually started at somewhere here and it moved almost close to theta. It takes 70 iterations to move to the global minimal error place, right? So if you see by 20th iteration it actually moved to the almost to the global error place. By 24th iteration, right, it actually kind of almost there. And 40th iteration, if you see the slope, I said that the slope is going to be high here, it's going to be a little low here, it's going to be even low, and here if you see 0.24. When slope is becoming very small, when you substitute this slope into this equation, what is happening here? The alpha is already small, the slope is small. When you multiply these two numbers, it becomes even smaller. When you subtract that, right, if you see this, it is changing at a fourth decimal place, right? If you see the next iteration, right, it will change at around eighth decimal place. So the slope became very slow. So what is happening when theta reaches here, right? The movement will stop, and at one point in time the line will not move anywhere. And I said while explaining the initial stages, the line should start somewhere here and stop at the middle or the best fit place. It should not surpass the data and try to find the thetas, right? I said that, right? So it is going to happen when your slope becomes almost zero, the subtracting element or the component will become almost zero, and the theta will not change anymore once it reaches the global minima or the best theta it found, the gradient descent algorithm found. So now, if you see this, right, this is how it is actually traveling. It started somewhere here. This is 100 line, this is 70 line, this is 50 line, this is 36 line, this is 24 line. Like that, it is moving, and ultimately it found its best theta, right? From here, even if you run 1000 iterations, it will not move from here because your slope almost became zero, and the term you are subtracting from theta is almost zero. So that's how the gradient descent algorithm works. And we'll see the notation and the math behind the gradient descent in coming session. Thank you.